we stuck on, okay? So now we're going to take half of this extra thing that we stuck on. So now the question is this figure double this figure?
No.
You're going to ace the final exam. What is, Baruch, what is the relation of the size of this figure to the original figure?
2 1/4.
2.25.
2.25, right? Because it's got an extra square, right? This one has got 4 little squares in it, and this figure has 9 little squares. So we want 8 little squares. Okay, or, now let's try this with Wertheimer. We want half. We got this one. We know this one is double, right? How can we get half the double one? There's some sneaky way to get it that produces a square. There's half of that subsquare. There's half of that subsquare, half of that subsquare, and half of that subsquare. So now the area of this has to be half the big sucker, right? So now we've got our square, and what line is it built on? It's built on the diagonal of the original square. Gorgeous, huh?
Yeah.
Absolutely.
Thank you. That was the right answer. Okay, and this is the bit that's so astonishing, right? If you say this is a unit square, then this is root 2, the existence of which was a scandal for Pythagorean mathematics. Right? So that a slave would be able to demonstrate, that somebody who knew no mathematics at all could see this, had to show Plato thought something extraordinary about his logic. As I mentioned in the class today, whenever I do Meno and do the proof, you go on to the next bit of the dialogue where Socrates is talking about methodology, and you'll be talking for 5 minutes, and from the back of the class, you'll suddenly go, oh! Somebody gets it, right? Somebody really sees it, right? And experiences it with a physical shock. This has happened to me year after year, an audible gasp, right? What underlies that experience, I think, is not only getting that the square double in size is built on the diagonal, but that this has to be the case. It's the case on Mars. What impresses is not simply the claim's truth, but its necessity. This necessary truth would seem to be something a metaphor cannot possess. Metaphors, we think, are creatures of linguistic play, not deductive logic. Surely there's nothing conceptually necessary about a claim like the heart is a red pepper. But let us think hard about this for a moment. Good poems, including poems like Sinclair's Red Pepper, which elaborates a single metaphorical insight, are notoriously difficult to teach. You got any teachers of English here? Good ones are hard, right? Yeah. You can ask any poet or sensitive English professor. You can build a tolerable lecture around a mediocre poem, which often requires lots of external information to make it comprehensible. But one often has the sense with a good poem that everything that can be said has been said, and perfectly, in the poem itself. Either you get it, or you don't. In this, it seems to me, good poems do resemble the simple visual proofs we try to teach students in ancient philosophy classes. Yes, there are some who grasp the Meno proof with a gasp, but there are others who don't see it at first, or even at second blush. If they don't get it, there's little I can do but say the same thing, walk through the demonstration, read the poem again. And when they get the poem, grasp its central metaphorical insight, there's often an expression of astonishment, just as there is with the theorem, a sudden stillness in the room, occasionally tears, These are not the same acknowledgments of necessity as we find in mathematics, but that is nonetheless what I believe they are. Their differences stem from the nature of the necessities compassed by the two domains. Mathematics, I believe, shows us necessary truths unconstrained by time's gravity. Poetry, on the other hand, articulates the necessary truths of mortality. It is time now to return to our initial questions. Whence the vision-altering power of some metaphors? And how is it that we are able to distinguish between such metaphors and arresting but mere linguistic confections? Metaphors, I wish to suggest, can be insightful in just the way that mathematical analogies can. They reveal to us unsuspected kinships between facts long known but wrongly believed to be strangers to one another. And, as in mathematics, the most fertile will often be those formed of elements drawn from domains which are far apart. This does not mean, as Poincaré notes, that we simply bring together the most disparate objects we can think of. Such a tactic can produce surprise, but it is surprise without depth, sterile, in Poincaré's word. It means that, as in the case of mathematical analogies, metaphorical power is a product of discernment, to borrow again from Poincaré. But discernment of what? I wish to propose that the correspondence between metaphors and mathematical analogies suggests that we distinguish between profound and shallow metaphors along the lines of a mathematical distinction between important or fruitful mathematical conceptions and unimportant ones. Here it is helpful to note that even a realist like Kepler, who believes that good mathematical analogies reveal truths about the actual universe, argues that the value of analogy lies in the most spacious field of invention that it opens. In other words, discernment in mathematics and, as part of this, the development of true analogies, whatever truth is there, consists in perceiving connections that point the way to yet other connections. Connections that point the way to other connections. The power, the value of analogy lies not in a definitive mapping of some territory, but paradoxically enough, in its freeing of the imagination for further discovery. To put this yet another way, a fruitful or important analogy is one that establishes a deep field of resonance. It might be objected that this proposal clouds the issue more than it clarifies it. The notion of a fruitful or important conception is so contested in mathematics that it cannot usefully form the basis of a parallel account of good and weak metaphors. For underlying questions about which conceptions will prove fruitful or important is a debate about the nature of mathematical creativity. And this is one that is hotly engaged right now in the literature. There are books coming out about it every year. Is mathematical creativity a form of discovery, or is it a type of invention? Mathematicians don't agree on this question. Couched in metaphysical terms, the question is whether mathematical entities and truths have an existence independent of the human mind that eventually discover them, or whether they are, as metaphors are often supposed to be, simply constructs of human discourse and imagination. Neither argument nor experience has yet been able to settle this question in the history of Western European ideas. As Demidov notes, the experience of the working mathematician supports both claims. It is not my intention to settle the debate. My aim is to suggest that, rather than rendering the comparison between powerful metaphors and fruitful mathematical analogies problematic, it may point yet again to a fundamental similarity obscured yet again by literary prejudice we are disinclined to examine. For what the existence of the debate between realism and constructivism in mathematics should suggest to us, given the correspondences we have noted, is that a similar debate